There are two different ways using which we can represent a graph. These are by using an adjacency list or by using an adjacency matrix. So in an adjacency list, what we do is that we can use a dictionary where the keys are the nodes and the values represent the neighbors. The key can be here. We can have A, B, C, and D has the different keys, and along their values we have the neighbors. For example, A is a neighbor of B. There is a edge from A to B. There is a edge from A to C. Therefore, the values uh, for A are B and C. In case of B, we have edge coming from B to D and a edge from B to A. So in B, we have A and D. For C, there is only a single edge that goes from it, which is from C to B. So along the C, we have B. And in case of D, there is single edge which is from D to B. So D has a value B. And here we can have the adjacency list representation for this same graph. Here we have four different vertex. So therefore we will need four different rows, and each row will represent a vertex. And the column will also represent the neighbor vertex. So for example, here starting from the first row, which is A, in A we have B connected. So the column for the B, which is the first column, since it is zero based indexing, is value 1 since it is connected. The C is also connected from A, therefore this is also 1. From A, D is not connected, therefore it is 0. Now coming for the B. From B, A is connected, therefore it is 1. From B, B is not connected. There is no self loop, therefore there is no edge that is coming from the same node to itself. That's why I'm keeping this value as 0. Okay, you can see the whole diagonal. The diagonal represent an edge from the node to itself, which I have kept as 0. Now for B, from B to B it is 0. From B to C, we can see that from B there is no edge to the C, therefore it is 0. From B there is an edge to D, therefore it is 1. Now coming from this, now coming for the C, from C to A there is no edge. From C to B there is a edge, and from C to C there is no, and from C to D also there is no edge. Now for the D, from D there is no edge to A, there is an edge to B, so it is 1, and from C to C it is 0. From C to D there is no edge, therefore it is also 0. So these are the two different kind of representations that we can have for a graph. For this simple graph, we can use a adjacency list in which we can use a dictionary where the key will represent our node and the value alongside that key will represent the neighbor. And in case of matrix, we can use a 2D matrix where each row will represent our node and the column will represent the neighbor node. Okay. So for any value Aij, where I is the row and j is the column, if Aij is 1 in list matrix, then that means there is a edge from ith node to jth node. Therefore, we can have random access in this array. We can find the value for Aij in big O of 1. So it is instant. Knowing if an edge exists between two elements, between two different nodes, is instant. Whereas in case of this list, if we want to find where there is an edge between two nodes or not, then we have to go through all of its neighbors. Okay, for example, if I ask a question, if there is a no edge between A and D, then I'll have to go for its neighbors and check if D is there or not. Okay, so this way of searching where there is a edge directly between two nodes or not, it is very much faster in matrix in big O of 1, whereas in case of graph it is not big O of 1, it is something else, which is big O of degree of the node. Okay, so in worst case it is going to be big O of n. For example, if A is connected to all the different nodes, In that case, I have to go through each and every node for the whole list, and then I can figure out whether the different node is there or not. Okay, so in this case, it is equal to the degree of that particular vertex. What is the degree? Degree is the total number of neighbors in case of an undirected graph, and in case of directed graph there are two degrees, which is in degree and out degree. I'll come to them later on. Okay, so these are the different ways using which we can represent graph using a adjacency list or an adjacency matrix. Here we have used list, but you can also use set in case of adjacency list, because if we want to have only unique elements, then it makes sense to use set. Now let's compare the adjacency list and the adjacency matrix. As I've already said, we can represent adjacency list using a dictionary of list or a dictionary of set, right? And for the adjacency matrix, we can do it using NumPy 2D array or a list of list. Okay, so if I'm talking about the space efficiency, then the adjacency list, certainly it's the superior one. It has it has less space complexity and is more space optimized. It has big of v plus e, where v is the number of vertex and e is the number of edges. This is the space complexity. In case of adjacency matrix, we know that we will need a 2D matrix where the number of rows and number of columns are going to be equal to the number of nodes. So the space complexity is big of n square. Now we know that since there are big of n square and there are like very few edges, then that means most of the values are going to be 0 only. So there a lot of space is going to be wasted in case of adjacency matrix if the graph is not a dense graph, meaning if there are not lot of edges, right? And in real world, where we have something like a Facebook kind of situation, there are a lot of people. There can be like 10,000 people, and you can imagine that for representing 10,000 people and their friendship, we have to use 10,000 into 10,000 size of matrix to represent their friendship. But in case of adjacency list, it will be very less. And also you can, it is logical that one person will not have 10,000 friends. One person will have like 100 friends, 200 friends. The number of edges are going to be very less compared to the number of nodes. Therefore the adjacency list makes more sense over here. And now looking at the edge lookup case, so the edge lookup is big of degree of v, or in the worst case it is big of number of vertices in case of adjacency list, because we have to go through each and every neighbor to the list of each and every neighbor to find out whether the neighbor exists or not in that list. But in case of adjacency matrix, it is very performant. We can have a lookup in big of one time from a matrix. We have random access. We can just look if the particular if matrix ij is 1 or 0. If matrix ij is 1, then that means that there is a edge from node I to node j. Okay, so this is it. As I've already said, the adjacency list, it is best for sparse graphs and large data sets, whereas the adjacency matrix, it is best for dense graph because it provides us performant lookup. And the degree of a node in undirected graph, it is a total number of its neighbors or the total number of connections that a node has. For example, if I go back here, I can see that a is if this is actually a directed graph, not an undirected graph. But if this was an undirected graph, then there were like no directions. If this was a simply undirected graph, in this case the degree of a will be 2 because it is connected to two different nodes. The degree of d will be 1 because it is connected only to one nodes, right? But it is a directed graph. The direction has a meaning. So in directed graph, there are two things. There is one thing which is called as in degree, and there is another thing which is called as out degree. Okay, so in degree is the total number of edges that are coming towards the node. For example, in case for b, it is one edge coming from this side, one coming from this side, and one is coming from this side. So in degree of b is 3. The in degree of d is 1. There is one edge coming towards it. The in degree of C, it is also 1 since there is only one edge coming towards it. But if I talk about the out degree, then the out degree of C is 1 since there is one edge going from it. The out degree of D is also 1 since there is one edge going from it. And the out degree of A is there is one going to B and there is one going to C. Therefore, the out degree is also 2 for A. Okay, so this was it about the different representations that we have for the graph. Now, before completing this chapter, first let's see code implementation of graph using Python. Okay, I have opened a Python IDE and here I have a sample graph, and now what we are going to do is we are going to create a graph. Now I will be using Python classes to implement the graph, and what we are going to do is basically for storing the nodes we need some sort of data structure. So let's do this first using adjacency list. Okay, so we are using adjacency list, and for that we'll just take a simple empty dictionary. Now it should have a method which is called add node, or let's just call it add vertex, and this is what we are going to have. It will take a vertex and then we are going to put that vertex in the graph. Serve.graph vertex, and it's an empty now. So one thing that we can do is that we can check for error handling if it's already there. If vertex is already there, in that case we don't have to do anything. But if vertex is not in graph, then what we are going to do, we are going to create a new vertex, and along that we have an empty list, and this list will be used to store all the neighbors for that particular vertex. And we can have another method which is add edge, and what it will do is that it will take two vertexes so that we can add an edge between those two. So what it will do is it will go into the graph, and for vertex 1 it will append vertex 2. And one more thing that we can do is that this add edge method, it can add an edge between vertex 1 and vertex 2, but we can take another argument which is bidirectional, meaning if this edge is bidirectional or not. If the edge is bidirectional, then there is going to be an additional edge from vertex 2 vertex 1 as one. So this is as saying in the vertex 2 also append vertex 1. In the neighbors of vertex 2 also append the vertex 1. So these are the two simple methods that we have in the graph. Let's create a graph. And now what we are going to do is we are going to basically add 4 different vertexes. Okay, so these are the 4 different vertexes: A, B, C and D. Let me update this. A, B, C and D. Now what we are going to do is we are going to add an edge. So graph.add underscore edge between A, between an edge between A and B. Similarly, we can see that there is also an edge between B and A. So what we can do is we can have an edge between A and B, and then we can also have an edge between B and A. But a short thing to do is simply saying that it's a bidirectional edge. And we can set it to true. So A is going to B and B is going to A, but A is also going to C. but C is not going to A. Therefore, it's a unit directional between A and C. Graph dot add edge between A and C. Right. So A is going to B and A is going to C. That's okay. Now let's search for B. B is going to A since there is bidirectional edge, but B is not going to D. Therefore, we are going to again add an edge between B and D. Now go to C. C is going to B and D is also going to B. So there is going to be C, which is going to B, and there is also going to D, which is also going to B. Okay, so we have added all the edges, but there's one more thing missing, which is we also want to see the representation of this graph. We want to see this graph, right? So let's also add a print method for this graph, and using this, what we are going to do is we are going to print all the different nodes and their neighbors so that we can see that we have implemented the graph in a correct manner. So for key, or you can say nodes, neighbors in self dot graph dot items, we can just print simply the node and the neighbors. Okay, so let's just run the code and add edge. It is missing one required position, which is bidirectional. So this bidirectional thing, it is actually a optional argument. So if it is not set to true, that means it is false. Here I'm not seeing anything. Okay, so that is weird. Let's see why it is happening. So graph, I have added all the vertex, I've added all the edges, but now I also have to print the graph. So I'll call the method graph.print, and here you can see A is connected to B and C, B is connected to A and D, C is connected to B, and D is connected to B. Therefore, we have correctly implemented the graph. Now we can also add some additional methods. For example, what will happen if we want to remove an edge from the graph? So let's do this. If there is a remove edge method, vertex 1, vertex 2. Now what will happen is, if there is vertex 1 as in, if there is vertex 2 in the vertex 1, in the neighbors of vertex 1, vertex 1, if it is there, then what we need to do is basically we have to just remove it. Okay, so self dot graph vertex 1 dot remove vertex 2, or other thing that we can do. Okay, so let's just do it like this, and let's try this thing. How about we remove the edge between A and C? Graph dot remove edge between A and C. So here you can see that the edge between A and C is removed, and A is only B as the neighbor. More things you can do is implement error handling. For example, what will happen if I try to remove an edge from vertex 1, between vertex 1 and vertex 2, but if vertex 1 is not there? Okay, so such kind of edge cases, they can be implemented. Initially we implemented the two most important methods, which are add vertex and add edge, but more methods can be added, which are remove edge, and if there is a something like a remove vertex, which is going to take a lot of effort not in the code implementation, but there will be many operations happening from it. For example, if I do remove vertex, then what will happen is that it will take a vertex, and then what we need to do is we have to go through each and every node and look into their neighbors and remove it from there. So what we have to do is for node and neighbors in self dot graph dot items, what we need to do is basically actually we don't need this, or we can make it even simpler. If we need just neighbors, then neighbors are the values. Okay, so this is as saying this. So what we need to do, if vertex in neighbors, then what we need to do is we need to do neighbors dot remove vertex, as simple as that. So suppose if here I try to let's just comment out this thing, we are not removing any edge, but what we are doing is that this time we are instead removing a vertex, and I say that we want to remove B. Let's see what happens now. So you can see that B is not there. It has gone, right? So B is removed as a neighbor from all the different nodes, but the B node itself is over there, right? So one more thing that needs to be done is in the remove vertex, we have to check if vertex is in self.graph. If it's there, then we have to simply delete it in the end. Okay, now let's run this and we can see that B is also not there. Now what will happen if instead of B we remove C? Let's run this code, and now A is the neighbor as B, B as the AD, and if we compare it with this, the C is not there, right? The C is removed. So these are the different methods that we had to implement. So in case of add vertex, what we need to do is we need to just add an extra element to the list at the end. So this is the adding is in big O of 1 time complexity. Okay, so it is very performant in the adjacency list. If we look at the add edge, then it is also very performant. We can see these are the single operations that are happening, right? So this is also big O of 1. So adding new element, it is very performant in adjacency list, and removing edge, this is taking some effort. For this we have to traverse through all the elements, for all the neighbor elements for that particular vertex. Okay, so we need to do that. Therefore it is big O of, we have to check it in vertex 1, since we are removing edge from vertex 1 to vertex 2. So this is big O of, it can be big O of n, where n is the number of vertices. Since if it's a very large list, then we need to go till the end to find if there is the neighbor element or not, meaning there is an edge or not, right? And in case of remove vertex, we need to go through each and every neighbor for each and every element. So if this is a dense graph, then there can be n into n different connections. So this will have a time complexity of big O of n into n, where n is the number of vertices, and in this case it is also the big O of n when we are removing the edges. Okay, so these are the different methods that we have for adjacency list. Now let's again implement this graph, but this time instead of using an adjacency list, we will be using an adjacency matrix. So in the matrix, we have to define the dimension. Therefore, we have to first define the total number of nodes that we have in our graph before we can add vertices or edges. So we will have another argument which is n, and n will define the total number of vertices. So graph here we can represent it using a 2D list, a list that will contain n list. So that is going to represent our graph. And here how we can add a vertex. So what we can do is essentially we can have essentially what we can do is actually this is like this. For I in range n, that means n times, we are going to have a array which is of size n. So this is how we will represent the matrix in the graph. And what we are going to do is we are going to add an edge, add a vertex. So how can we know that a vertex or a node exists or not? Well, we can keep it really simple, and we can just say if the particular if a particular element that is denoted by the ith row and ith column, if it is 1, that means the ith node is set. Meaning if the self dot graph vertex and then again vertex, if this thing is 1, that means we can see that there is a vertex. And removing a vertex can be we will come to it later on, but first let's complete the very basic methods, which is the adding vertex. Adding vertex is big O of 1. Okay, and adding an edge, this is also big O of 1. It's a really simple method. What we will do is we will have the graph vertex 1, vertex 2 set to 1. Okay, so since Aij represents since matrix Ij represents an edge going from ith node to jth column, if it is 1, that means there is a edge from ith node to jth node. So in this case, it is vertex 1 to vertex 2. If it is bidirectional, then what will happen? If it is bidirectional, then there is going to be between vertex 2 and vertex 1, there is also going to be an edge, right? So this is the logic for bidirectional. And adding edge, still in this case, it is just 2 operations, so it's a big O of 1 time complexity. And how do you remove an edge? It is really simple. It is also big O of 1. How? If we want to remove vertex between edge between vertex 1 and vertex 2, what we need to do is basically we just have to set self dot graph vertex 1 vertex 2 to 0. Since it is set to 0, that means there is no edge between vertex 1 and vertex 2. So it's a big O of 1 operation. And how can you remove a vertex? If we want to remove a particular vertex, then what we need to do is we want to remove this vertex from all of its neighbors, right? For all the different nodes, we have to say that this vertex is no more there. So how can I do that? Firstly, I can say that vertex self dot graph vertex and then again vertex, this thing is equals to 0, meaning this one particular vertex does not exist. And then what we can do is that we can just remove this vertex from all the different neighbors. So for I in range, also for this we need to set this as a class variable, right? So we can access the dimension in different methods. So for all the different n nodes, we have to remove this. Okay, so what we need to do is we have to set self dot graph and the node from the and the edge from ith node to the particular vertex should be equal to 0. Okay, so this is how it is going to be, and the logic for printing the graph, how it's going to be. So since the graph is in the matrix, we have to go through the matrix for I in range n, which represents the ith, which represent our node, and j represent the neighbor for the ith node. So for j in range n, so what we can do is we can say uh, does the ith node exist or not. If ith node does not exist, then we can just move forward, meaning if self dot graph I, if this thing is 0, then continue, meaning I don't want to travel check for its neighbor since it doesn't exist. And what we can do now is for j in range n, we can say if uh, what we can do is we want to print it, right? So firstly we will print the current node that we are traveling through. So this is I, and is at the end. I just want a space, an arrow like that. And for all the jth element, I want to check if there is an edge from I to j or not. So if self dot graph, if from I there is an edge to j, then that means it is something that I have to print. Okay, so I'll just print j, and I say and equals to just space. And at the end, when I have printed all the elements for the ith node, then I'll just have an empty line so that it is much more visible. Okay, so now this time here what I can do is, instead of using something like a, b, c, and d, I can use numbers like 0, 1, 2, 3, 4. So now I will replace a with 1. Okay, so I'll replace a everywhere with 1. Okay, I'll replace b with actually I should replace okay, I can do it like this. So I'll replace a with 1, I'll replace b with 2, and I can replace c with 3. Now I'll replace d with 4. Okay, so in this at this time, when I'm creating a graph, along with the when I'm creating graph, I'll also have to give the dimension for the adjacency matrix that I will be using in the graph. Now, since I have used one base indexing, in order to store these 1, 2, 3, 4 numbers, I'll need a matrix where the rows and columns, they are 5 in size, because for the matrix it will be 0 base indexing. Okay, so I have done something like this, and now let's add, I've added all the edges already, so I'll just print the graph. So it says in range n, so there is a mistake here. Instead of n, it is self dot n. Okay, and let me see if it's somewhere else. Self dot n over here, and also self dot n over here. Let's rerun the code, and again this time we have printed the code. So we have 1 and 2 connected, we have 1 and 3 connected. Okay, and this time actually I'm also printing the same node here over again. So since I can handle this logic within the code, and what I can do is basically here why it is printing is because when we have added the edge vertex, what we are doing, we are setting this value to 1 to represent that yes, this vertex does exist in our graph. Okay, so instead of using this, we can use something else. For example, the the benefit of Python is that it is dynamically typed language, so we can use it something like this. So if it is plus, then we can just totally skip it. So here what we can do is that we can do two things. Actually, we don't have to also do this. What we can simply do is that over here, when we are printing the graph, what we can do is for j in range n, we can also check if I is equals to j, then in that case just continue. Okay, so let's rerun, and then we have that thing removed. So 1 is connected to 2 and 3, as you can see already, and 2 is connected to 4, okay, which we can see, and 2 is also connected to 1 through this bidirectional edge, and 3 is connected to 2, and 4 is connected to 2, which we can see over here, right? And what will happen if I remove an edge between 1 and 3? Let's do this. So 1 and 3, the edge is removed, so 1 is only connected to 2. That's what we can see. Okay, so it is working as expected. Now from this, what will happen if I remove the vertex? Let's just uncomment this thing and print the original graph. Now in this graph, I can see that 3 is the neighbor of 1 and 3 is also a node. So let's see what will happen if I remove the vertex. So here 3 is completely gone and 3 is not a neighbor of 1 as well. So this is also implemented. So here what we can see that printing always have in the printing, we always have to go through all the nodes, right? Here we have to go through all the nodes and edges, so it is big O of n square. Printing the graph is big O of n square because we have to traverse through the matrix. And the remove vertex, this is very fast, right? So whenever we have to remove a vertex, actually this is we have to do it in big O of n. Why? Because we are iterating for each column within that row for that particular node, and we have to set them to 0. So it is in big O of n. Okay, so removing an edge, it is a big O of 1, and adding an edge is also a big O of 1, and adding a vertex is also a big O of 1. So this is it. This is much more performant. The edge removal is much more performant, but adding edge vertices, these different operations, they are very performant. The lookup is in big O of 1, but the issue is that it takes a lot of space, and if there are not too many edges, then that means the most of the space will go wasted since it will only have 0 values.